That's not, okay, there we go. Okay, so this is a different way
Why is the door ajar? I'm curious.
of calculating it. What basically this does is, instead of calculating everything with one equation, which you can kind of set it up, and if it's right, that's okay. What you can do is to calculate each of the energies that you know to begin with separately, and then just sit there. Remember that one of the kinetic energies is going to be zero. It doesn't have to be, but I'm going to make the promise, so it either stops whenever it ends up, or it starts from rest and falls down. So this also reverses the situation, but it's a different way of doing it. So what they say in this case is this: there's a 250 kilogram satellite that's going to be launched from the surface of the Earth, reaches its maximum height. It's going to have another rocket that's going to produce the orbit. This isn't really the way they would normally do this. What they do is send them in an arc to begin with, and they just kind of end up at that place. This is just minimal values. What they're saying is they're going to send it up to this point, and if it just stopped, it would fall straight back down again. So when it reaches this point, they fire another rocket that actually gives it a velocity to keep it in the orbit at that point. So if you start out thinking about the overall energies that it has, initially it's going to be at this point, and it's going to have a potential energy because it's a radius, but they're also going to give it a velocity so that it can move upwards. So it's going to have a kinetic energy. Eventually it's going to reach this point. That's the initial. This is going to be the final position, but what they wanted to do is to stop at that point and then have a different rocket shoot the start to get the orbit part. So what we can do first of all is this: if we start out by thinking, I need to know the potential energies in the equation, you can calculate each one individually. I know where it is on the surface of the Earth, so I'm going to say the initial potential energy is going to be on the Earth. It's going to be minus g, and we'll put in the specific things. The mass, the big mass in the thing would be the mass of the Earth, and I know that that's 5.97 times 10 to the 24th, because I've used that enough times. And then the satellite is 250 kilograms. Sorry, do that. And then also, I have to divide by the radius of the Earth. And the radius of the Earth, I've done that enough times. I know that's, remember, it's 6.37 times 10 to the 6 meters. And in this case, you don't have to square that. So if you put in the g, the 6 times 10 to the 11th, and 5 minus 7, 250, and something like that, this number. It's going to be a negative number, and it's likely to be pretty big.
$1.56 times 10 to the 10th.
Okay, so we'll make it 1.6 times 10 to the 10th, you said? Yeah. Okay, and these would still be joules, and a joule isn't a large amount of energy, but there's 10 to the 10th of them, so the total is. The next thing is, there's also, we know what the final position is, so there's also a potential energy there, and it's the same thing. It's still going to be 5.97 and all that other stuff, 10 to the 24th. And it's going to be still 250 kilograms. The only thing different is it's going to have a different radius, and in this case, it's going to give you the radius of the orbit. We don't have to add the Earth to it and anything like that. It's 9.6 times 10 to the 6th meters for that.
Times 10 to the 10th.
And you expect that to be, okay, just not that you need to know this numerically here, but notice that it moved upwards, so it should have more gravitational potential energy here than it does here, and it doesn't look like it does, except remember these are negative. This is a less negative number, so it's increased by having less negative energy at that point. Now, that -1 I'll kind of remember. I want to scroll up so I can kind of see the next thing that's going on here. But once you've calculated those energies, it might be a little bit easier for you to see how to do the mathematics in the equation part for this. If you want to calculate the launch speed, then basically you picture this. What it has initially is a kinetic energy and a potential energy. And what it has finally is just a potential energy, because when it's in orbit, it stops, its kinetic energy is 0. So I can put that in, but it's going to be 0. And if I put in 1/2 mv squared, this is the 250 mass of the satellite. I'm trying to find out what velocity I need, but the initial potential energy is what I had there. It's negative 1.6 times 10 to the 10th, and that's equal to this other potential energy. It's negative 1.0 times 10 to the 10th in joules. And basically from here, you can just add this to the other side and divide by the 125. So it's a little bit easier to do the mathematics than in the one long equation. Is the only difference. So if you do that, this is going to be something like, you don't really have to write steps individually here, but I'll write them kind of like this. If I add this to the other side, it's going to be 0.6. It's like 1 minus 1.6. It's 0.6 times 10 to the 10th, and you divide by 1/2 of this, divide by 125, and then take the square root, and that would give you a velocity. Again, it should be probably thousands of some meters per second.
6,900.
6,900, okay, so 6,900, and then you put meters per second at the end. So, again, just the mathematics might be easier to do in step-by-step this way than the other way, but either way, works as long as you set it up correctly. Okay, so that's it. That's the last example. And